There's really 3 parts to chapter 6, if you'll remember. So we actually started chapter 6 before spring break. That's law of sines, law of cosines. So I have quiz corrections for that I still need to hand back. If I have time at the end of class today, I'll do that. But that might be something that you start reviewing if you have extra time this evening or tomorrow evening. No ambiguous case, when to check for the second triangle. Know the rules about law of cosines, find the biggest angle first before you leave it and go to law of sines, those types of things. And then when we came back from spring break, we were in those 2 sections all about vectors. So you should be able to do all that vector work that was on the vector quiz. I'll be able to give those back to you guys tomorrow. And now section 6.5 is kind of like another little random section, trig form for a complex number, and then we're going to do lots of things with the complex numbers. But it does have a lot of similarity to vectors. So as we work through our notes, try to frame in your mind, oh, that's like this in vectors, or that's like this. And then it doesn't seem like you're learning something brand new. We're kind of using the same stuff, okay, rather than reinventing the wheel. So we're going to get to trig form of a complex number, but first we're just going to review complex numbers. Okay. The standard form for a complex number that you know from Algebra 2, I'm going to say z equals, z is the common letter for a complex number, and its standard form, this should look familiar to, is a plus bi. So previously, before you knew about complex numbers in Algebra 2, you thought the only numbers that existed were the real numbers, all the numbers that you always learned. And we introduced the imaginary unit in Algebra 2, and we say, actually, there's all these other numbers, and we're going to call the big set the complex numbers. So every complex number is made up of 2 parts. There's a real part and an imaginary part. The set of complex numbers has now all the numbers that you know about. It has imaginary numbers, but it also has real numbers in it. The real numbers like 1, 2, 3 are really 1 plus 0i, 2 plus 0i, 3 plus 0i. So they are really complex. So complex numbers is the big thing. When you're graphing complex numbers, they might be imaginary, which would cause trouble for us on the XY coordinate plane, which is called the Cartesian plane, because X and Y are all real numbers. So you have to graph a complex number on the complex plane. And the complex plane has your horizontal axis as your real part, and your vertical axis as your imaginary part. This will be important that you can plot one of these complex numbers in the correct quadrant, because we're going to be finding angles, so we'll need to know which quadrant that angle is in. So for example, let's say I'm going to plot a plus bi. It's just like plotting a point. How did I get to that complex number, a plus bi? I went a units on the real axis, because that's my real part. And I went b units on my vertical axis, because that's my imaginary part. So in this case, because I landed in quadrant 1, both a and b must have been positive. Now, last thing real quick as a review of complex numbers, we're going to talk about absolute values. So just as a review from regular numbers, if I ask you, what's the absolute value of -3? You say 3, and I'll ask why. Because it's the distance from 0. So we're going to do absolute value of a complex number. The definition of absolute value does not change. It's still the distance from 0. So if I'm looking at my complex number, a plus bi, out here on my complex plane, and I want to find its absolute value, I want to find its distance from 0, so I'm going to label that the absolute value of z. And what do you suppose you're going to be using to find the absolute value of z? The square root of a squared plus b squared. That's distance formula, Pythagorean theorem. What does that look like in vector work? Magnitude makes sense. Yeah. I'm not reinventing the wheel. I want to find the distance between 2 points on a right triangle, so I'm going to do Pythagorean theorem. One quick thing to note about that a squared plus b squared, when you put b in, remember your standard form is a plus bi. This is only the coefficient b. This is not bi. So don't put bi in and square it, because then you'll get b squared I squared, and we know that I squared is equal to -1. We shouldn't get any negatives under there. So it's only the coefficient b. Okay, let's practice these things. You're going to work with your pod members to see if you can plot the complex number and if you can find its absolute value. So its distance from 0. Go for it. We've got z equals 3 minus 4i. Plot and find its absolute value. Okay, I see good work as I'm walking around the room. Your point should be plotted in quadrant 4. You're going right 3 down 4. 3 is the real part, -4 is the imaginary part. Real is horizontal, imaginary is vertical. And then when you do absolute value, that would be 3 squared plus -4 squared underneath the radical, square root 25, so our absolute value is 5. One thing that I did notice on the vector quiz as I'm grading it is some people like in vectors they were doing like a magnitude, so they would say like the magnitude of v, and then they would work it out, the square root of, let's say 3 squared plus -4 squared, and when they got to 5 they would answer like this, like to say the magnitude is 5, but you don't need those magnitude bars, like you did that, right? So the answer should just be 5. Okay. Same thing for absolute value. If you do the absolute value work right here, you don't need an absolute value around the 5 anymore. Just like when you do 2 plus 3, the plus sign goes away. So something to note, and you'll see that when you get those back tomorrow. Okay, now we're going to get into the good parts, where we change it into trig form. So we called it standard form. On the previous slide, it's currently the only form of a complex number that you know, a plus bi. And we also call that rectangular form. That's going to help us like in our next chapter when we do polar coordinates as well. What rectangular form implies is that you can only move, like think about a rectangle on the coordinate plane, you can only move left, right, up, down. So those are the only directions you're allowed to move, which is why that's called rectangular form. Rectangular form, the easiest way I could say, how are you going to tell the difference between rectangular form and trig form is, rectangular form, you're going to be able to identify an A and a B. It's going to be like numbers. So like 3 minus 4i, 2 plus 3i, 1 minus I, 1/2 plus 3/4 I. Those are all in rectangular form because I could say A is 1/2 and B is 3/4. When we switch to trig form, instead of having an A and a B, it has R and theta. So it's written in a different form and uses different values. It's not going to use the left, right, up, down. It's going to use rotation, the angle, and distance, the R. Now, we call R and theta modulus and argument. Okay, modulus and argument. And make a little note when you do your argument, just like when we were doing vectors, your only acceptable thetas are between 0 and 360, so that everybody would know immediately which quadrant it's in. If it's between 0 and 90, it's quadrant 1. If it's between 90 and 180, it's quadrant 2. 180 and 270, 270 and 360, quadrant 3 and 4. Okay, so our job is to figure out if we have A and B, how can we get R and theta, and also vice versa. If we have R and theta, how can we get A and B? So we can go in and out of both forms. The answer is trig. So we're going to draw ourselves a picture. Plot a complex number. I'll call this A plus B I. In order to plot that, I went A units to the right. I went B units up. We just talked about the distance from that point to 0 as the absolute value, which, if you think back to chapter 4 trig, that's going to represent your sort of radius, if I gave you a point out in space. So there's my R, my modulus. And theta, the angle, is always going to be happening right here around the origin. So what did I end up drawing? A right triangle. Okay. So, if I have A and B, let's say I have rectangular form, and I want to put it into trig form, I got to come up with a way to write A and B with R's and thetas. Anybody see any trig in there that will help us get A and B in R and theta? Emma, I have one. Are you willing to share? Oh, cosine, sine, you're thinking A times cosine theta. So I'm going to start back at like the basics with just cosine in the picture. If I did the cosine of theta, that's equal to adjacent over hypotenuse, which would be A over R. So what does A really equal? R times cosine, as opposed to A times cosine. So A equals R times cosine theta. And then how would you get B? Sine theta, right? If we set up sine theta equals what? Opposite over hypotenuse, B over R, then B is equal to R sine theta. So remember, I just asked you, if you have A and B, how can you write them with R's and thetas? We just did. What part of vectors does this remind you of? R cosine theta, R sine theta.
Oh.
that component form with magnitude and direction angle. I mean, it's the same thing, right? So don't like reinvent the wheel here. The horizontal component is r cosine theta, and the vertical component is r sine theta. Okay, now we're going to write the trig form, okay, by making a substitution for a and b. So instead of saying a, we're going to write r cosine theta. Someone call this is trig form now. Plus, and then normally I would have bi, but b is r sine theta. Now I am going to rearrange this a little bit. Usually you'll see a mathematician, instead of saying r sine theta times I, they'll put the I in front. So I'm just going to do that. But multiplication is commutative, right? So it doesn't matter what order I multiply them. The only reason like a lot of people would do that in math is so it doesn't look like the I is on the angle. You can see that I is just like r sine theta is a coefficient to I. Okay, this is trig form. Right there. It looks like a plus bi, except a is r cosine theta and b is r sine theta. The vertical and the horizontal and vertical components. Now, there's other ways that people will write trig form. So, when you look at these two terms, what do they have in common? R's. You might see it written like this: r times cosine theta plus I times sine theta. So you might see that like in your homework tonight. You have the option, if you want to distribute the r as you write it down, you can. But we could still easily pick out like what's modulus, what's argument, right? And then, you know how mathematicians are super lazy sometimes? Like Miss Frankie? We don't want to write that down. That's a lot. Cosine theta plus I sine theta. So we made an abbreviation. Okay? It looks like this. R kiss theta. Sounds like kiss because it's cosine, so it's a hard C.
Oh, it's cosine, sine.
Yeah. Yeah. You see that? Okay, now, anybody else who's not in our class, any Algebra 2 student who would see this might think that KISS is a brand new trig function, right? Like cosecant, secant, and cotangent. It's not a trig function by itself. It's a shortcut to writing cosine theta plus I times sine theta, because we're lazy. So Miss Cronky's going to be writing down a lot because she's lazy. You could write it if you want. You definitely have to be able to look at it and know what it means, but if you want to write it out the long way, that's fine with me too. They're all right. R cos theta. So I'm going to put that one in. A special bubble. Okay, I like that one. Okay, so that'll be how I'm going to get it into trig form, or that is what trig form is. Okay. Suppose we were working at it like we wanted to write A and B with R and theta. So A is R cosine theta, B is R sine theta. If we're in trig form, so we have modulus and argument, and we want to put it in rectangular form, so we want A and B. Well, I'm doing this the opposite way. Suppose we're in trig form, so we have A and B, and we want to go into trig form. Okay, so we want modulus and argument. We don't know what they are. What's an equation you could write to solve for R in that picture? What do you know about R? It's the square root of a squared plus b squared. It's the absolute value of the complex number. It's the magnitude of the vector, if you think about it like vector work. So we know that r is equal to the square root of a squared plus b squared. So if you ever need to find modulus, do absolute value of a complex number. And how would you find theta? if you knew A and B?
Tangent of B over A.
The tangent of theta would be equal to B over A, opposite over adjacent, and then to solve for theta, you would do the inverse tangent. This looks like direction angle of a vector. So now we have on the screen, we have, like if you know A and B and you want to get R and theta, you're going to do modulus argument, basically Pythagorean theorem, tangent. If you have it in trig form and you want to go back to rectangular form, you're going to be doing R cosine theta, R sine theta to get your A's and your B's. So let's do some examples so you can see this put to work with numbers. We're going to write 6 minus 6i in trig form. What form is it currently in? Standard form, rectangular form. This is A plus BI. Okay, so we have A's and B's. We want trig form, which we know is my abbreviation, Arcus theta. So tell your group members what you need to find. And then find it. No, they get hired at a salary of 30%. And answers should be exact. Notice.
6 radicals.
In your
You just take out 36.
I heard as I was walking around, a lot of people said, find R and theta. You need those things for trig form. So if you have A and B, how do you find them?
45. That's not right.
It's add 360. So it's.
You still have to, at the end there, put it in trig form.
Okay, what?
6 right. 2 cosine.
4. You're already in point 4. Negative 45. All the way around.
6 right. 2
Oh. Do we have to like simplify?
Oh,
Do we have to
Okay. So, like I said, most people said find R and theta. R, we're going to be doing absolute values, square root a squared plus b squared. That's going to give us what we call the modulus. Okay, same thing as what we would think about like the magnitude of a vector. Now, when you get the square root of 72 on this one, make sure that you simplify that radical if possible. That's 36 times 2, so that's going to be 6 square root 2. If your final answer has a radical in it, your radical should be simplified. That's our always rule. Okay. Your argument, theta, if you plug that into the calculator, the negative 6 over 6, that's the inverse tangent of negative 1, which in your calculator it'll tell you negative 45. That's not an acceptable argument because it's not between 0 and 360. So to figure out the actual argument or actual angle right there, remember, think about where you would plot 6 minus 6i. On the real, you'd go 6 to the right, and on the imaginary, you'd go 6 down. So if that's in the fourth quadrant, what should you do to negative 45? Add 360. If it ended up that your complex number was plotted in quadrant 2, then you would add 180. So how do you know when to add 180 or 360? it depends on where the point is. So you gotta think visually. Okay, I got R, I got theta. My answer, R kiss theta, is 6 square root 2 kiss 315. And that's my favorite version because I'm lazy. If you don't like that version, you could write it all out, right? So the longest version is 6 square root 2 cosine 315 plus I times 6 square root 2 sine 315. Can barely fit it in there.
If you do that, do you have to simplify it?
No, you leave it like this.
Okay.
Because if you simplify this, you go back to rectangular form, 6 minus 6i, which leads me to my next example. We gotta write this in rectangular form. So think about what Hannah just said. She was asking, should I simplify? If I write it out like cosine 315 and all that stuff, do you have to simplify those trig functions? And I said no. Because if you do that, you go back to rectangular form. So when you're in KISS form, expand your KISS form and evaluate your sines and cosines, and that'll put you back in rectangular form. That's probably the easiest way to go about switching back to rectangular form. And give me answers in exact values, no decimals again, please. You know how it is. All I'm going to do to switch back to rectangular form is expand my KISS form. So it's r cosine theta plus I times r sine theta. Then I'm going to think about 2 pi over 3 on my unit circle. What's the ordered pair for 2 pi over 3?
-1/2.
-1/2.
Radical 3 over 2.
Positive radical 3 over 2. And remember on the unit circle, the x is cosine and the y is sine. So now I just evaluate. So that's going to be 8 times -1/2. This is 8 times -1/2. Plus I times 8 times, what, square root 3 over 2? And 8 times -1/2 is -4. And 8 times square root 3 over 2 is 4 square root 3 over 2. I usually write that as plus 4i square root 3. I don't like my i's to be behind my radicals in case someone thinks it's underneath. So make sure when you're drawing it, if you put I behind, that's fine. But make sure it doesn't look like it's underneath the radical, or I'd take off for that. Square root of I is different than I. Now, did anybody do that differently than me? The other way to do it is like go back to, I think Emma started us for like finding A and B. A is r cosine theta. B is r sine theta. So you could like break it up and just say r is 8, theta is 2 pi over 3. Do those separately and then plug them into A plus BI. But it's essentially the same thing, right, as expanding. Any questions for me? Anytime you're working with things on the unit circle, give exact answers. If that said like the cosine of 5 pi over 7, I don't know that. So if I wanted to change it into rectangular form, I would use my calculator. Pay attention to your mode. If it was 5 pi over 7, I should be in radian mode. And then I would type it in and get decimals. Okay, so be aware that that's an option. Okay, last thing. There are 2 additional formulas I'm going to give you today. They can be used to multiply and divide 2 complex numbers that are in trig form. You already know how to multiply and divide complex numbers in rectangular form. You did that in Algebra 2, and you did it again for semester. So now we're going to look at it from a trig form. I'll let you write these down before I say too much about them. Now, I will say on first glance, these formulas look a lot worse than they actually are once you figure out what everything is. And they're much better than your alternative, which I have over here on the sideboard. If you were going to take 2 complex numbers, z sub 1, z sub 2, and they were in trig form, so they were like r kis theta, if I expand out my kis theta, the first complex number would have like an r sub 1 and a theta sub 1 for its modulus and argument. And then the second, it might not have the same modulus and the same argument, so we would call it like r sub 2 and theta sub 2. And then I would have to FOIL this out. And when I FOIL it out, some things might cancel. I'll be able to use my sum and difference formulas from chapter 5. So remember, like the sine of u plus or minus v, the cosine of u plus or minus v. And that's why in these product and quotient rules, do you see that you're adding the 2 angles or subtracting the 2 angles? That's your sum or difference formula at work. So if you wanted to, you could FOIL all this out and do a whole bunch of simplifying with formulas, and it will come out to be this thing. Okay, so this is just our shortcut, and it's much nicer. You know, you'll have to know these for Friday's test, but what I remember about multiplying 2 complex numbers, you multiply the modulus, and then you add the arguments, right? And then it'll just be in KISS form. And then the opposite is true for division. Divide the modulus, subtract the 2 angles. Okay. I will say this, theta sub 1 plus theta sub 2 and theta sub 1 minus theta sub 2 must still be between 0 and 360. So if you add them and they go over 360, or you subtract them and they're a negative value, use a coterminal angle. So you could add or subtract 360. Okay, but this will work out really easy, okay, once you see it in action with numbers. So here's an example similar to what you might see on your homework. Find the product of 3 KISS 60, 4 KISS 30. Now in your book, they might write it out with the KISS form. They might write it out in the extended form. You can go in and out of either form that you prefer. You'd still be able to recognize the modulus and the argument. Okay. So z sub 1, z sub 2, I know I should multiply my modulus, add add my arguments. So what two numbers am I multiplying? 3 and 4. And what two numbers am I adding?
60.
60 and 30. So to multiply those two complex numbers together, I will get 12 kiss 90 in trig form. That is way easier than foiling that stuff out, yes? Okay. If I wanted rectangular form, we would do like we did on that last example, expand and evaluate. So that would be like 12 cosine 90 plus I times 12 sine 90. Well, the cosine of 90 is 0, and the sine of 90 is 1. So that'll just be 12i. Which makes sense, because if your angle is 90, you're going to be on the vertical axis going up, and if you go up 12, that's 12i on the complex plane. Now, how will you know which form to write it in? I would just read your directions. If it doesn't say one or the other, then any of those answers are acceptable. If it says in trig form, then it should be in trig form. And you might see like a division problem. Division problem shouldn't be too terrible. Let me see what I got up here. Yeah, this one. Find the quotient. I'll just divide the modulus, subtract my angles. So that'll be 4 kiss, what, 45? 45. And this would be its trig form. In rectangular form, that'll be what? 2 square root 2 plus 2i square root 2. If I had those flip-flopped, so when you subtracted I got negative 45, then add 360 so that it's 315. It has to be between 0 and 360. So just the same way as it was for direction angles with vectors, it is true for complex numbers. All right, your homework's on your gold sheet. Really important that you do your homework tonight and you feel better about the KISS form and the complex form expanded. Because tomorrow we're going to do powers and roots. Those formulas may be a little bit more involved than our product and quotient formulas.